Alright, Julia data analysts, we're back for a second round. In the previous video, we loaded in files from the California Department of Education. Now we're going to go ahead and analyze these files in some very basic ways. And that'll be some subsetting, some joins, and then plotting, some very basic plots to see what's in this data set. Okay, so let's get started by introducing a few tools that we're going to want for manipulating the data. Here at the DataFramesMeta GitHub, this is where they have the documentation for the DataFramesMeta package. This package basically offers you a lot of macros like order by and subset and by and with and each row and by row and so forth. So each of these is a macro, and what that means is that inside the macro the syntax has some slightly different meanings from what it would have in regular Julia. So how does that work? Well, each macro is going to essentially compile down to some Julia code that performs a task, such as subsetting the rows of a data frame or sorting them or whatnot. And inside the macro, you can refer to variables in the data frame, the data frame's column names, using a symbol. So in Julia, a symbol is something like this. Let's take a look at in Julia. If I type foo, okay, what I get is the colon means quote, and then foo is a symbol. So this is the symbol test score. Okay, it's different from a string, right? Test score is some bytes in an array of some sort that uses UTF encoding, UTF-8, and represents text. A symbol represents something a little bit like a variable name. It's a structure, not an array. Okay, so it's a parsed representation of a symbol or of a word. And Julia uses those for parsing its own code, but you can also use them in other contexts. And in this case, we're going to use them to reference variables in the data frame. Okay, so let's head back to to here, where we can see that here's some basic operations. We can sort a data frame, we can get subsets, we can transform by row, we can do selection of just certain columns. We can transform by making new columns, by doing transformations on old columns, combining groups together if you've got a group data frame, and so forth. These are sort of operations that you might do in the tidyverse dplyr context if you were using R. I'm sure there's some Python equivalent as well. The split, apply, combine concept, where you structure a data frame into groups, and then you apply functions to the variables within that group, and then you combine the like taking averages or medians or doing some other summaries is done with the by macro. So you get grouping and combining all at once. Okay, so we want to use these, and DataFramesMeta is a core package for us. doing data analysis. So okay, let's go over to our Julia code again. The last thing that we did was we fixed the test scores. They had been parsed as strings, and then we turned them into a floating point number or a missing value. Now I've restarted VS Code since then, so I'm going to need to go through and run everything so that we're up to date. So I'm going to go ahead and just run that and run this. Oh, hit the wrong button. Alt enter runs the whole block. Alt enter this block. Alt enter this block. Alt enter this block where we read all the files, and then we fix the floating point or missing values. So now we're waiting for it to run through, and we need to get to here. And that should happen pretty quick because we got those arrow files in the cache that we talked about last time, so we don't have to do any downloading and we don't have to do any parsing, and voila. We're up to here. We got 3.8 million rows. What we're going to do is we're going to pull out 3 districts of interest. We're going to pull out Pasadena Unified. We're going to pull out Alhambra Unified, which is slightly south of Pasadena, and Glendale Unified, which is slightly west of Pasadena. And these are all, communities in Southern California, in the Pasadena general area. And we're going to take a look at what they are doing. So let's talk about how we do that. The first thing we're going to want to do is subset the entities table to find out which schools are in this school district. And specifically, we're going to subset the entities table. We're going to find rows where the district name is not missing, and also the district name is equal to this, right? And also the school name is not missing. Okay, so rows where it's Pasadena Unified Schools and we know what school it is. And part of the reason for this is that they have summaries of the whole district which don't have a school, and we don't want to include those. We want to have just the breakdowns by individual school. And we do the same thing for Alhambra Unified and Glendale Unified, and each of those goes into entities table that's relative to those districts. Let's talk about the syntax a little bit more clearly. We are broadcasting the not operator. The bang here is the not operator, logical negation. And when you have an operator like a exclamation point or the and symbol, you broadcast it. Instead of by putting the dot at the end, you put the dot at the beginning, and that's only for operators. So dot not means take this vector of things and logically negate it. Why is that a vector of things? Because we're broadcasting the is missing function using this across the variable that's named district name, and this is a symbol, and inside a DataFrames macro, a symbol like that refers to a column. Okay, so that makes it, and a column is a vector of values. That makes it very easy to refer to column names, and is one of the major reasons why DataFramesMeta exists, is because by doing these macros you can make the syntax of working with data much easier. Okay, so anything that's not missing the district name, dot and means take this vector over here and item by item calculate the logical and with the values in this vector here. And this is saying look at the district name, which because of the quote colon there refers to a column, and dot equals equals this particular string. Okay, so dot equals equals means compare every element of the district name to this string. And then we're going to also AND it with not missing vector. Let's go back here for school name. Okay, so check to see if the school name's missing, make sure that it isn't, and anything where all of these things are true by logical AND, that's the subset we're going to take. Okay, the similar thing, so that gives us the entities we're interested in. So to get the tests we're interested in, we'll take just certain fields from the entities table. Okay, so at select means make us a new data frame that is built from this data frame by taking just these column names. Okay, and then we're going to left join that to the test scores data. Okay, left join means every row in this table on the left will be taken, and we'll look for whether or not there's a row, all the rows on the right that match in some sense. Okay, match on what we're joining on. When we say on equals school code, what we mean is match the school code in between the two tables. And then if it's missing value, then these two things are not equal. Okay, so if we have missing on both sides, it's still not equal. We don't match missing to missing. If we have missing on just one side, then it doesn't match, basically. Okay, so we're not interested in missing values. And we're going to do this for PUSD tests. We're going to do it for Alhambra tests and Glendale tests by just changing which entities table we're going to look at. Okay, so in the end, this is the test scores for the entities associated with the particular tables that we have up above. Okay. There's two kinds of tests we're interested in. Test ID 1 is the English test for the smarter balanced assessment or something. And test ID 2 means the math test. How can we verify that? Let's take a look over here. This is the Julia extension, and if we click there, it'll connect us to our workspace here, our Julia workspace, the REPL, called Julia REPL. And we can examine variables that we have here. And in particular, the data frames, the test data frame, if we click on this little icon here, it will pull up a nice tabular form of this data frame. And you can see that test ID 1 means the Smarter Balanced English Language Arts Literacy. And the test ID 2 means the Smarter Balanced Mathematics. And those are the ones we're interested in. I believe these are older tests, or maybe they're, some of them we still may be doing, like maybe the science test is still something that they're offering, but I think most of these have to do with earlier types of testing. So Smarter Balance is what they do these days, and that's what we're looking for. So test number 1, English, and test number 2, mathematics. And I'm just mainly going to look at mathematics, but we're also going to have some graphs of the English. Let's take a look at what we're going to do. I wrote a function to plot each school in its own plot. And I'm going to apologize a little bit here. I have not made an effort to make these plots beautiful yet. I want to spend some time walking you through, beautifying plots, because those are important skills to have. But we'll need to look at documentation for the plots library, and we'll need to just turn that into its own video. And so some of these plots may have, overlapping text or labels that are not, too big or in poor locations or whatever. But we're here to plot stuff and just look at it and say, do we care about this plot? And you're only going to tune your plot if you really care about showing it to somebody. And after you've seen it, maybe you say, you know what, it's useful to look at, but we're not really going to use it too much, so we're not going to clean up the plot a lot. So in the early stages, it's always a good idea to kind of spend your time figuring out which plots you want rather than making each plot beautiful. Okay, so we're going to plot all the schools. If we give it an entities table and the test scores table, it's going to run through and do this stuff, okay? So we get to learn some more iteration. So in general, in Julia, for loops are not necessarily just written by having an index that goes from 1 to 10 or whatever. For loops are written using iterators. Okay, so we want to do this for loop, and we're going to iterate over something. What are we going to iterate over? Well, we're going to iterate over simultaneously the values 1 and 2, which will also be paired up with English and math. Okay, so we have these two. This is an iterable container. It's a vector of integers, and this is an iterable container. It's a vector of strings, and vectors are iterable. In other words, they can be put in an iterator position, and then Julia knows how to step through them. If we take the function iterators.zip and we give it 2 iterators, okay, which we have, then it will return a new iterator that gives you the pairs. Take 1 and English, and then 2 and math. Okay, so this thing will become 1 in English and then 2 in math. Okay, so this name will get bound to the first item, and then this name will get bound to this item from the second item. We're going to let PL equal an empty array. This is where we're going to shove our plots. And let just means create a new variable binding or set of variable bindings in a new scope. And then inside that scope, we're going to do this stuff. So first we're going to iterate over, which test, and then we're going to iterate over each row of the entities table. Okay, the each row function gives you an iterator over entities rows. So SCH, the school, will be a tuple of all the values in each row of entities. The data frame we're interested in plotting is going to be the subset of the test scores, where the school code equals sch.schoolcode. Okay, so we're iterating through each entity, like each school, and we're looking. So we're going to take a subset of all the rows where we have the school of interest. The subgroup of students that we're interested in is 1. Let's take a look at students table. The demographic ID 1 means all students. Okay, so the subgroup ID is the name of the demographic ID in the test scores table. So we're looking at all students in that school. The grade is less than 13. There's something to do with, I think 13 is like a summary of average overall grades or something. In any case, we don't want that too much. The test that we're interested in is whatever the test ID currently is. Remember that we're iterating over the test IDs, 1 and 2. And none of the scale scores are missing, right? So we take that subset of data that comes from this school, is this particular test that we're interested in, has no missing data. Now, some schools just don't have data. Specifically, they might not have math data, or they might not have whatever. They don't have any scale scores at all. Maybe the school only has 3 students because it's an independent study school, and they don't give averages over less than whatever it is, maybe 10 students. So they don't have any data. So anyway, if we do have some data, then what we're going to do is we're going to make a new plot. P is equal to @df means evaluate all this stuff in the context where these kind of symbols refer to the columns of this data frame. So @df is a macro in the stats plots. Here, let's go look up here. Stats plots exports that macro. So using the data frame, do a plot of grade and mean scale score. Grade on the x-axis, mean scale score on the y-axis. X will go from 3 to 12, and y will go from 2250 to 2750. That seems to be sort of the range where the scores are. We're going to group the students together by test year minus grade minus 3. So this is a cohort grouping, right? In grade 3, grade minus 3 would be 0, and so this value will be test year. In the following year, people will be in grade 4, so grade minus 3 will be 1, and will be in the following year, so the following year minus 1 is the original year. So this is the year in which they entered grade 3, so if that makes sense. So that forms a cohort. So they get plotted with their own color as a group. Our legend will be false, so we're not going to plop up a little legend of what we're plotting, like groups, for example. Make the size 250 by 250 pixels, and we'll title it the given test name and then the school name. Okay, with a line width of 3, so it's a little bit easier to see. And then after that, we've plotted these lines. Plot will give you lines. After that, over the top, we'll scatter plot points. Okay, the bang here means that we're actually modifying the previous plot. So we're plotting grade against mean scale score, but this time it's points because it's a scatter plot. And we're doing the same grouping, and you'll find that although we're grouping it that way, the colors are different, and we'll just have to go into how to fix that in a different class. And here we don't want any like line around the point. Okay, so, and then we push this plot P into the PL array. Okay, so this array of plots, just push it in and move on to the next one. We iterate over that, and then when we're done iterating over all the schools, right, each rows of the entities, we're going to display the plot of all the plots put together with this ... Okay, what that ... means is it says take the values in this array and splat them into the arguments of plot. Okay, so there might be like 25 plots, and so we're going to basically say plot this plot and that plot and the other plot and the other plot 25 times, as if we had written them here with commas in between. Okay, so that's splatting. This semicolon means after that point we're talking keyword arguments, and we're just going to tell it to make that 1500 by 1500 pixels, and then we'll go through and do the whole thing. So we plot all the tests, all the schools, and we're going to do that for PUSD and Alhambra. Okay. Looks like we've got a redundant subgroup, information here. That's okay. So let's run the whole thing. When we run it, bang. Hopefully we don't. I may not have run the previous function. Let's run this one first. So we'll make our tables. It might take a little while to evaluate. This is the first time we're evaluating any of these DataFramesMeta macros, so they get compiled the first time. Not too bad. And then let's plot this next set of plots. As we do this, what will happen is, again, the first time we make plots, everything takes a little longer. This is called time to first plot, and it's because we're compiling things. But here we go. We've got two large plots. What you can see here is this is the plot of the math scores of Alhambra, and then if I hit the left arrow, I can go get the math scores. Sorry, English scores of Alhambra, and then a left arrow math scores of Pasadena, and English scores of Pasadena. You can see down here these are plots 1, 2, 3, and 4. So I kind of can go through it by clicking or by using the arrow keys. So what we've discovered is that in Pasadena, the structure of the schools is pretty much that they've got, elementary schools, which are only testing in 3rd, 4th, and 5th grade. Then they've got some middle schools, which do 6th, 7th, and 8th. They've got some middle high school combos, 6th, 7th, 8th, and then 11th, because they don't test in 9th or 10th or 12th. And then they've also got just some high schools, so they only have the 11th score. Okay. The color codes here have to do with cohorts, right? So these are people that entered 3rd grade in 2014 or whatever. Entered 3rd grade in 2015. They have a different color, and the colors for the dots and the lines I don't think match, and that's something we'll talk about later. We'll fix these kinds of things by explicitly giving colors. But let's see what we see. The first thing is, we've got this this one school that goes K through 8, and so the math scores are increasing, trending up, and they go all the way through. These other elementary schools, they just go K through 5, so they're tested in 3rd, 4th, and 5th grade, and you can see that there's some growth in scores, which you would like to see. So, but you can see that some scores start low, like 2350, and other schools in 3rd grade they're already at 2450, and some of this is related to socioeconomic effects, like education of the parents and how much income they have and so forth. So that's English. Let's take a look at math. Math is kind of interesting. There's much less growth here, right? This school is flat. I mean, not completely flat, but pretty flat. This school has some growth here. This school has some growth here, but they start at a lower value mostly. This school here is a middle school, and it's very flat. McKinley has some growth, but it's kind of tapering off into an asymptote. And then you can see that these two schools that have middle and high school, they're pretty flat. They go up a little bit in the middle school years, and then they're kind of the same. Not very much improvement by 11th grade. Let's compare that to, here's English. Let's do the math comparison. Comparison for math in the Alhambra district. So all of their schools are K through 8 or high school. So they're K through 8 schools. You can see, a lot of growth. There's a lot more growth here, and we're starting maybe at a higher level, like 2400, and then ending up at almost 2600. And you go back and you look at, someplace like McKinley is doing pretty well, but it's starting at 2400 and winding up at 2500 or something, as opposed to the 2600 that they were seeing in the other schools. Some up here in the 2650s, 2650s. So these students, here's almost 2700 in Brightwood. Now, these students are doing better. Is that because of the schools, or is it because of the mix of the kinds of students that they have? Those are the kinds of questions we're interested in. All right, so So far we've just shown you how to make some plots, and we can color them by a cohort, using grouping and so forth. And we've got all kinds of problems. We've got these, problems with overlapping text here. Maybe the font should be bigger. We should make this, 2 lines or something. We should fix the color scheme and all of that. Maybe labels. Labels might be good, but having a lot of labels in a multi-panel plot can just take up a lot of space. So it might be better to just label this as a, as a footnote, or footer to the overall plot. So we raised some questions, though, right? Some questions like, is the growth that we're seeing in some schools varying? This is sort of a little bit of growth. This is reasonable growth. This some of these are pretty stagnant through here. That's not much growth there. It's sort of flat. These are the English language scores. So in the math, this is really flat right here. That's pretty flat. That's pretty flat. So this is just completely flat. So what's going on? Let's break it down a little bit. So we're going to go in and, just having done this set of plots, we ask the question, like, how much does this depend on socioeconomic grouping? And that's what this describes as. We can use different groupings. And the grouping I'm going to use is the education level of the parent. Okay. Group number 90 is students whose parents have no high school diploma. 91 is students whose parents have a high school diploma. 92 is students whose parents have attended some college but not graduated. 93 is people who have graduated from an undergraduate degree. And 94 is grad school graduates. Okay, or at least they attended grad school. I don't know exactly, whether they have to have graduated here. So those are the education levels we're interested in. I create a dictionary using these pairs. So a dictionary is a data structure that you can index by these values and get back, what it's associated with. That lets us go through and make some plots and let's look at just test ID 2. That's math. Let's look at test ID 2, or create a function which plots some groups by education level, each of these education levels within the school. So we're going to iterate across the rows of the schools table that we pass in. This will be the scores table, and this will be the district name so that we can stick it in the title. We will create a data frame that's a subset of the scores. According to, we want the math tests, we want the school code to be our current school, we want the subgroup to be within the 90 to 94 range. That's this range here. So we're going to take all the different subgroups. Then we're going to create a plot using the @df macro for our new subset data frame. We're going to scatter plot the points, grade versus mean scale score, using a certain x limit and certain y limit, and we're going to give it a name saying this particular district, and then a new line, and then the math at this school name, and then by parent education level. We're not going to use labels for these data points. We're going to use a marker size of 3, and the overall thing will be a certain size in pixels. And then we're going to go through and loop through the education levels between 90 and 94. We're going to subset our data frame to have just the education level with no missing data. If we got less than 4 data points, we're just going to skip it. If we just output some information while we're going, we're going to collect up the different grades that we're interested in, which is in between the minimum grade and the maximum grade that we have data for. And as long as we do have data for several grades, at least two, we're going to run the Loess locally estimated regression line through the grade and scale score data for the subset of students with the particular education level we're interested in. And then we're going to plot the grades that we collected, and we're going to map this function here, which takes an x value and produces the prediction from the Loess fit for that x value. This right arrow here means this is an anonymous function which maps inputs on the left to outputs on the right. And we're going to map that across the available grades. Okay, so this is the grades itself, and this is the predictions for the averages for that subset of students. We're going to label it with the name of the education level and give it a little bit of a thick line, and we'll keep looping, looping. When we finally are done, we're going to display P, which is the last plot that we made, which remember where plot bang here means overwrite. We're going to write a line over the top of whatever we had before. Okay? And then let's just run that for each district. Let's take a look at what that looked like. That's a lot of stuff to explain, but let's take a look at what we get. All right, this is each school, and we get something like looks like this. Students with no high school education in their parents, that's this group here, this line. Some high school diploma is this green line, all right? Some college is the purple line. Parents have college graduate, that's this sort of goldenrod or whatever that is line. And then this teal color is for parents who have some graduate school education. What you're seeing is obviously math scores are going up on average for kids whose parents are more educated. Not necessarily surprising, but it can be surprising how big that effect is. This is a score difference, of 100 points on a scale where 2400 is kind of what in particular third grader might typically get, and 2700 is a very good high school graduate. Most of the difference between different students can be explained by their parents' education level. We can kind of go through, we can see, here's not much growth in the middle school in Glendale. Kids pretty much flat. Yes, they have different values, different levels, depending on their parents' education level, but they're really not growing their mathematical sophistication. At this school, yes, they're growing. They're getting more sophisticated in terms of their scores in third grade versus fifth grade. So good. Here's a middle school, a K through 8 middle school, and there's definitely some significant growth here. Now you notice that not every school has all these groups, right? There's probably one or two kids in the non-represented groups, but unless you have a big enough group, they don't even give you the average because of privacy issues. So anyway, we can run through like all of these. We have a lot of data. Some of these, it doesn't make any sense to fit a line through a bunch of stack of points where you've only measured in 11th grade because it's the only time you measured. But here's an Alhambra. We can see that there's definitely different kinds of growth, different shapes, and the levels are always sort of split by educational attainment of the parents. In Pasadena Unified, this McKinley school is a K through 8. It's one. I think it's the only one And you can see a big difference between the no high school diploma students and the graduate school educated students, where the parents have grad school education. So we in general see this pattern repeat. And there's always a separation between the different parental education data. Why is this happening? This is happening because there's no points in the middle, right? There's just like a vertical stack of points here and a vertical stack of points here, and for whatever reason there was no some college grads available in 7th grade, maybe because in the years that we have available, the number of students decline below the threshold for reporting or something like that. So we get some ugly stuff like this, and this tends to happen when the data is super sparse. You're missing points. Okay, that's a lot of stuff to look at. Here's some middle to high school. You can see that there's kind of an upward trend, and then it kind of flattens out. An upward trend, and then it turns over, flattens out. We don't have any data in the middle here, but we know that there's kind of a certain shape here, but we have to continue it smoothly, so we sort of turn over. That's why these predictions in the middle, that's what they are. They're predictions. They're not necessarily good predictions. They just are based on the Loess prediction method. Okay, so we've got a lot of different graphs that we can look at in a lot of different schools, and we broke it down individually by school. Let's stop there.